So in this video lesson, we're going to have a look at projectile motion. Projectile motion is going to be different from our regular motion that we've learned so far in kinematics because projectile motion is going to be dealing with curved motion. So all the motion we've looked at so far in kinematics has been motion that is going in perfectly straight lines. And sometimes we change direction. We go from west to north, but all of that motion is still traveling along a straight line. Projectile motion is when we are not traveling horizontally or vertically or along some tilted direction in a straight line, but instead we are traveling at in a curved type of motion. So the perfect example is how a football travels. So if we just draw the ground here. So a football, or let's use a soccer ball. Okay, so either one. And so if we kick a soccer ball, the soccer ball is going to curve up and then it's going to start to curve back down before it falls on the ground some distance away from us. Okay, and so that's our curved motion. And so projectile motion is going to be dealing with anytime we're dealing with curved motion. So that's if an object is like kicked up in the air, if something falls off of a table, that's a great projectile motion. Or if something gets like launched off a ramp. So say we are, driving off a bridge and we're trying to jump the bridge. So we drive up the bridge and then we launch off the top of it. And that's gonna end up being this projectile motion. So when we're dealing with projectile motion, the problem is that we have some vertical motion and we have some horizontal motion happening at the same time. So at any given point, we are going so far horizontally and so far vertically. And so every different point is actually a little bit different. So sometimes we're traveling a little more or less horizontally or a little more or less vertically. And so every part of our motion is a little bit different. And so we're traveling horizontally and vertically at the same time is the problem. So with our regular motion, we've been looking at just traveling either horizontally or vertically. But in projectile motion, we're traveling horizontally and vertically at the same time. Okay, so some important equations when we're dealing with projectile motion is that our initial x velocity is going to equal whatever our original velocity is times cos of the angle at which we are launched up at. And then the same is going to be for VIY, so our initial vertical speed or velocity is going to be our initial velocity times sine of the angle that we're launched up at. These are equations that you have to memorize. They are not on your formula sheet, okay? But they will be the same every time we are doing projectile motion. So for projectile motion, they never change, okay? And the one thing that I want to show you is that when we are being launched up, this will be our angle here. So if we're being launched up from the ground, we should have an angle at which we're being launched up from the ground at. If we actually have something that rolls off a table, so if we just draw a little picture here, so say we have like a ball or something like that that rolls off a table, in that case, the theta is actually equal to 0 degrees. So we could be launched up at an angle or down at an angle, that's a possibility too. But we also could just roll off the side of a horizontal desk or table or anything like that. And if we do, that means our angle is actually 0 degrees. Okay, so since we are dealing with both horizontal and vertical motion at the same time, we have two other equations that we use with projectile motion. And these two are on your formula sheet, so you don't have to memorize them. So the first one is that our delta dx, which is our displacement on the x-axis, is going to be our initial velocity on the x-axis times our time. And then our equation for the y-axis is that the delta dy, so the displacement on the y-axis, is our initial y velocity times our time, and then minus our 4.9, and then delta t is squared. Okay, so these are on your formula sheet. You don't need to memorize them. Okay, so no need to memorize them because they are on your formula sheet. And the reason the equations look different is because on the x-axis, we actually have no acceleration. Because in all of these problems, we are going to be ignoring wind resistance, air friction, that sort of thing. It's a little too complicated for us to take into consideration. But on the y-axis, we have acceleration due to gravity. Okay, so the reason that those two equations look different is because on the x-axis, we will have no acceleration. And on the y-axis, we're only going to have our acceleration due to gravity. And so our acceleration due to gravity, we know is actually 9.8. But if you remember what this kinematic equation normally looks like, usually there is a 1/2 there. And so 4.9 is actually half of 9.8. And so that's how we just used our regular kinematic equations to create these new equations for projectile motion. And that's where that 4.9 is coming from, because it's half of our acceleration due to gravity, because that was originally 9.8. Okay, so let's try a practice question. So in this practice question, we are going to have a table with a marble that is going to roll off the table. Okay, and the initial horizontal velocity, so we're actually given VIX, is 1.93 meters per second. And the table is 76.5 centimeters tall. So for part A, we're going to try and find how long the marble is in the air. So that's going to be in time. For part B, we're going to find the delta dx. So we're going to find how far away from the table the marble actually lands. And then in part C, we are going to find the final velocity on the x-axis and the final velocity on the y-axis. All right, so starting with part A. Since we are looking for the time, I think we are going to use our delta dy equation. Okay, and in this case, just sort of off to the side here, since the marble is falling off the table, it has an angle of 0. So that means our VIY would have been whatever the initial velocity was times sine of 0. And sine of 0 is 0, which means our initial y velocity would just have been 0. So we're able to plug that into our delta dy equations. We also want to make sure that our delta dy is in meters, right? We want everything to be in meters and seconds, or meters per second. So we're going to change that 76.5 into meters. Okay, so that works out to 0.765. But also, I want you to see that the displacement is going to be negative in the y direction. So we're going to actually land lower than where we started. Okay, so the marble is going to land below the table, and so that's actually going to be a negative value. VIY, we said, was going to be 0, and then we've got the rest of our equation there. So that means we end up with negative 0.765 is equal to our negative 4.9 delta t squared. So we're going to divide both sides by 4.9, negative 4.9 actually. So we have negative 0.765 divided by our negative 4.9. So that's going to give us 0.156. And then we're going to square root. So we get 0.395 seconds as our time. Okay. In part B, we're trying to calculate delta dx, and so we're going to use our formula for delta dx, and we happen to have Vix, it was 1.93, and our time is 0.395 seconds. So there we're getting 0.762 meters. So the marble is going to land about 76 centimeters away from the table. Okay. Oh, sorry, we're on part C now, not part B. So then in part C, we're looking to find the final x speed and the final y speed. Now, here's something amazing in projectile motion. The final speed on the x-axis is the initial speed on the x-axis. In projectile motion, we are ignoring our air resistance, and so we have no acceleration on the x-axis. But that also means we have no deceleration. So we're not speeding up or slowing down on the x-axis. So our speed on the x-axis, or velocity on the x-axis, is not changing. For our VFY, we're going to need to use a kinematic equation. But we just want to make sure we use a kinematic equation with only our y values. So since we know the acceleration and the displacement, and we know the initial y speed, I'm going to use this equation. So VFY squared is equal to VIY squared plus 2. Acceleration needs to only be the y-axis acceleration. And then my delta D needs to just be my y displacement. So my VFY squared, we knew that the VIY was 0, so that's going to be 0 squared. Our acceleration on the y-axis is just acceleration due to gravity. So that's 9.8 meters per second squared. And then our delta dy, we figured out already, was 0.765. Okay, so then our VFY squared is going to equal, we're just going to do some multiplication here, so 0.765 times our 9.8 times 2, and so that's going to give us 14.99, and we're just going to square root both sides. So we're going to end up with a VFY of 3.87 meters per second. So that's going to be our final speed on the y-axis. All right, so we're going to try one more practice question. So in practice number 2, a baseball pitcher throws a ball horizontally. The ball falls 83 centimeters while traveling 18.4 meters to home plate. So we are going to try and find the initial horizontal speed. have the ball. Okay, so we're going to draw ourselves a little picture here. So we have our baseball, and this is the ground. And so the baseball is being thrown horizontally, but eventually it's going to fall to home plate, okay? And so the distance that it travels to home plate is 18.4 meters. And so that is our delta dx. That is the range of the baseball, or the horizontal displacement. And then vertically, we know it's falling 83 centimeters. So that's our delta dy, okay? And so we're going to use our delta dy and our delta dx to help us find that initial horizontal speed. Now, the other thing we know is that the angle is going to be 0 degrees because the ball is being thrown perfectly horizontally to start, which means it's not being thrown up at an angle and it's not being thrown down at an angle. So the angle must be 0 degrees. So that means that our VIY, even though we don't know what the VI is, we know that it's going to be times sine of 0, which means our VIY is going to be 0. Okay, so we can use the delta dy equation first. And so we can plug in our delta dy. Remember, it's got to be in meters, and it should be negative because we're landing below where we started. And our VIY would be 0. So we're going to use this equation to help us find our time. So we end up with negative 0.83 is equal to our negative 4.9 delta t squared. So we're going to divide both sides by negative 4.9. So we get 0.169 here. And then we're going to square root. So we get 0.41 seconds is our delta t. Okay, and so we are looking for that initial horizontal speed. So we're going to plug that into our delta dx equation. So delta dx is Vix delta t. We know our delta dx was 18.4 meters. Vix is what we're looking for. And now we know our delta t is 0.41 seconds. So we do our 18.4 divided by our 0.41 seconds. So our initial horizontal speed is going to be that 45 meters per second. So that's the speed at which the baseball is leaving the pitcher's hand horizontally. Okay, so that's it for projectile motion. There is some practice to do with projectile motion. And just a reminder, those two equations with delta dx, delta dy, you don't have to memorize. They're on your formula sheet. But the equation for Vix and Viy, you do need to memorize. They are not on your formula sheet, and you need to know them. So you need to know that cos theta goes with the Vix, sine theta goes with Viy.